Chemistry. I'm your instructor, Dr. Suhas Gaudi. I'll be teaching BSc 5th semester Physical Chemistry course on spectroscopy. Here is the outline. So in this lecture, I'm going to cover only the application part of the microscopy. So the application of microscopy is to determine the bond distance in polyatomic molecules. So which molecules has more than two atoms in it. So how to calculate the bond distance between two atoms, that is the application of microwave spectroscopy. So that's we are going to see in this chapter. So let's start. So consider the gaseous linear triatomic molecule of carbon oxysulfide. So here we are going to consider only one example of molecules, that is triatomic molecule, that is carbon oxysulfide. So for which we want to determine two bond distances between oxygen and carbon and sulfide. So there two double bond is there, so we want to calculate the bond distance between two. So what are the methods? So this can be done by isotopic substitution method. So in this molecule we are going to substitute isotopic atom. So here instead of sulfur we are going to so first molecule is oxygen 16, carbon 12 and S32. So these are the three types of most abundant atom in respective elements. So oxygen, carbon and sulfur. So here if you consider as a linear molecule, so here we are going to study only rotational spectrum, that is microwave spectroscopy. So here if you apply that particular microwave to the molecule are going to rotate around its axis of rotation, that is center of gravity. So in this molecule the sulfur has 32 weight and 16 and 12. So this if you combine together, so it will come as a 28 and this is 32. So your center of gravity has to be lie in between carbon and sulfur. So it's more towards the sulfur. So in order to get balance in both way. So here the point P we are considering center of gravity. From that we are going to measure the all three bond distances like R1, like this P to C is the R1, P to O is R2 and P to S is the R3. So that are the bond distances. Moving further, since the center of mass is at P, so from where the various distances are measured. So this point is P, that is a center of mass or center of gravity. From that we have to measure the all distances. So from that we are getting this equation number 1. So that is mc, mass of carbon, into R1 plus MO, the mass of oxygen, into R2. So if you multiply this mass and this distance and this mass and this distance, that is R2, so that will be left hand side will be always equal to the right hand side. That right hand side is ms, mass of sulfur, into R3. So from this center of gravity or center of mass we are getting equation number 1. Now we are calculating moment of inertia for the whole molecules, carbon oxysulfide. For that we are getting this equation. So the I equal to mc, that is mass into distance square. So each atom mass and distance between from center of gravity, so that is the square of distance. So that is mc into R1 square plus MO, mass of oxygen, into R2 square and mass of sulfur into R3 square. So all this will be addition. So from that we are getting equation number 2. Now from this figure we can see that so R2 is nothing but your addition of carbon oxygen plus this R1 distance. So if you make addition together, so you will get the R2 distance. So from that we will get this bond distance between carbon and oxygen. And for R3, so this RCS, the bond distance between this and this, if you minus R1 value you will get the R3 value. So From this equation you will get the carbon sulfur bond distance. So that is the equation number 3, where RCO and RCS are the two interatomic distances to be determined. So these two bond distances we want to calculate. So by substituting equation 3 into 1, now we have to substitute this R2 and R3 value in equation 1 as well as equation 2. So what we are getting, that we will see now. So if we substitute this R3 value and R2 value in equation 1, so here instead of R2 you will be having RCO plus R1, and for R3 you will be having RCS minus R1. So from that you are getting this equation. If you rearrange this equation, you will get this MC plus MO plus MS. So all R1 terms we are taking into left hand side and remaining are right hand side. So that is RCS and RCO terms. So this is equation number 5. So the moment of inertia is given by so whole these three mass we are considering as a molecular weight, that is M, capital M, that is MC, MO and MS. So all atom mass will be considered as a molecule mass. So if you put that capital M over here for simplicity, from that you will get this equation. So that is equation number 6. So R1 equal to MS into RSC minus MO, mass of oxygen, into RCO divided by M, that is capital M. So this from equation 3 into equation 2. So now we add that R1 and R2 and R3 value in equation 2, but here now we are going to substitute equation 3 into 2. So then what we will have, so that moment of inertia term is there. So instead of R2 we have to put RCO plus R1, and for R3 we have to substitute this RCS minus R1. So now we have to expand this equation. So what we will get, so substituting R1 from equation 6 into equation 7, so we, for simplicity, we will get equation number 8. I equal to MS into R square RCS minus M naught RCO square plus 2M naught MS into RCS RCO minus MS RCS square divided by M. So from equation 8 we will get RCO and RCS distance. So only two unknowns are there in this equation. So these two RCO and RCS, we required one more equation. Now what we'll do, we assume that after isotopic substitution into the molecule, the interatomic distances will not change. So applying this assumption to the O16, C12 and S34, the molecule, we obtain a similar expression for the moment of inertia I dash of the molecules. Now there's only sulfur. In previous case we have only S32, but in this case the S34 will be there. So from that we are going to calculate the moment of inertia. So from that you will get one kind of moment of inertia. So here I and this is I dash. So two equation and two unknown, that is RCO and RCS. So from that we can determine the RCO and RCS from these two equations for the same moment of inertia. So only moment of inertia we are going to change because of masses. Remaining all ball distances will be the same. That is our assumption. We are going to see the reported bond distances using microwave spectroscopy. So as you can see in this table, so there are pair of isotopic molecules are there. So we have seen the first example. So for that we have RCO bond distances in Armstrong 1.1647 Armstrong, and for a carbon sulfur bond we have bond distance in 1.5576 Armstrong. So these bond distances came from these two different isotopic substitution. So instead of sulfur 32 we have used 34. So like that you can change the isotopic value isotopes between for carbon, for only for uh, carbon, and for only for oxygen. So like that you will be having four different types of bond length. So these small differences in bond length causes by changing the isotopes. So this due to changing in isotope we have got different bond length. So these differences are due to zero point vibration whose amplitude depends upon the masses of the atoms. So thus major bond length changes upon isotopic substitution. That's why we observe bond length changes. So here we came to end of this lecture. So that is the these are the references for images and for contents. There are four books are there. So thank you for kind listening. See you in next lecture. Till then, happy learning.